We're going to use our F13 vector, negative 4.3 newtons times I plus 6.1 newtons times J once more. And this vector looks a lot like our F12 vector, but it isn't. This is a very common type of application of a dot product. So this is now our displacement vector, and if you remember back far enough, that displacement vector that gave rise to the F13 force, and just coincidentally we're going to use that displacement vector. That's going to be, that displacement vector was 9.5 centimeters in the x direction, 10.5 centimeters in the y direction, so it's 9.5 centimeters times I plus 10.5 centimeters times J. Now you should understand that it's very easy to calculate the dot product of two vectors once you know their components. So this dot product is going to be calculated in a very simple manner. I'm going to tell you what this means and give you a little bit of background, but I don't expect, and this thing keeps going in and out of focus. It's not me, it's not the board. We stay in focus, but the camera goes out of focus. Okay. So I'm going to tell you right away that F13 dot delta S is a measure of the energy expended, or if we prefer, the work done by the F13 force if it acts through the displacement delta S. Now, what's that mean? That means is let's say we're moving the rubber bands apart. Then if we want that force to act through this displacement, we'd have to move everything this way. Okay, and in doing so, since this vector has a component in the direction of delta S, we're actually going to have to push a little bit in this direction. Now we're also pulling in this direction, so we're pulling parallel and perpendicular to delta S, but only the part of our pull that's parallel to delta S expends energy. Okay, the other might make my muscles tired, but I'm not actually expending energy. And we can actually measure that if you put me on some, not so heavy thing anymore, but let me pull in this direction with a force that's big enough that through a displacement that's big enough that causes me to get out of breath. Okay, the closer this force is to the direction of delta S, the more out of breath I'm going to get. If the force is perpendicular to delta S, I might get a little out of breath because there are physiological reactions associated with it, just exerting a force, but not much, hardly at all. And of course, you could do this too. But I don't like to use students for guinea pigs. Why is this thing going in and out of focus? If there wasn't anything written here, there'd be a reason for this. Anyhow, let me try to stay in the picture, and I hate to do that to you. So that we have this. Now I'm going to actually go off camera and write a little more, and hopefully the now let me write a little more right here. So as before, and I've kind of exaggerated this angle as I did before. This isn't a good 77-degree angle with our delta S. Okay, and this vector, if you recall, has exactly the same direction as the F13. It's at 48 degrees. This one's at 125 degrees, and this angle is 77 degrees. Okay, we have this vector projection, and if we multiply this vector projection times delta S, that's actually going to give us the same thing as this vector multiplied, the dot product of this vector with delta S. And we'll see a little bit about how that occurs also. So again, it's this component of this vector that does work. Come on, let's come on back into focus. Come on. Okay, here we go. Okay, let me get some more stuff up on the board so maybe we keep focus. Now, everything I've written down, in addition to hopefully keeping the camera in focus, is completely straightforward. Just trivial calculations and quotes, not that necessarily remembering all these expressions and what they mean is trivial, but the application is trivial. Okay, the dot product of F12 and delta S is simply what? I component times I component plus J component times J component. Make sure you understand why in terms of the original definition. But when we multiply I component by I component and j component by j component, well, this comes out something around -40, and this comes out something around 60, and this gives us 64. That's not right. Let me go back and double check a couple of things. Okay, I've made the correction. I actually used machinery to do this, and that's always a bad idea, and I didn't check it in my head until I started saying it because I thought I'd put the right numbers in. Hopefully that never happens to you, but I hope you always do the calculation in your head to get an idea of what it should come out close to. And that was really stupid of me because this vector has a magnitude that's not a whole lot different than the magnitude of old F12, except in units of centimeters, where that was in units of newtons. And the numerical magnitude is only, a little less than 20% more, so that the number we get here should have been just maybe 20% more, a little less than 20% more than the 20 that we got for the dot product with different units. So that was kind of ignorant of me. Okay, I could have just deleted that part of the clip and redone it, but I want you to see that kind of thing and how you can correct it by using your head rather than formulas, uncomprehended formulas and machinery to do your arithmetic. Sometimes the machinery is necessary, but usually you should be able to get a good order of magnitude calculation. Okay, that's a little better than order of magnitude, but you understand what I mean. Okay, so in any case, the units come out newtons times centimeters. And the calculation, again, is extremely straightforward. A newton times a centimeter is a unit of energy or work. Usually that would be written work energy. I like to mix things up sometimes. But it's an unnamed unit. We don't really have a name for the newton centimeter. And if you understand units, newton is an SI unit, centimeter is not. We name the unit newton meter. Now, a newton meter, meter being 100 centimeters, a newton meter is 100 newton centimeters, so newton centimeter is 1/100th of a newton meter. And the newton meter is a named unit. It's an SI unit, and we call it the joule. So the newton centimeter is 0.01 joule, so our work here would be 0.23 joules. I'm not going to get into that. I'm going to keep it in newton centimeters, but there's a connection there. And you might as well get aware of it right now. It's not that difficult. Okay, so our projection onto delta S of F13 now. Because I mentioned, if we multiply this projection by this displacement, we should get the same result, actually. And the reason for that is not deep or mysterious. You can work it out in terms of the meanings of these formulas. It's well worth doing. Okay, so F13 dot delta S divided by the magnitude of delta S. What's that mean? That's just equal to this side of the triangle, if you remember why. It's because F13 dot delta S is magnitude of F13 magnitude of delta S times cosine theta, so that this times cosine theta is going to be this. Not going to write that out. We've already discussed that. You should make sure you think through that. You really want to understand this. And then we multiply that by delta S over magnitude of delta S. Why? Because that's a unit vector in the direction of delta S. And that unit vector, of course, is just the same as before. That's the vector 0.67, 0.74. And I'm not going to redo that calculation. Just do that here. 10.5 over 9.5 arc tangent gives you, well, it gives you 48 degrees, I'm sorry. If we do the sums of the squares of these, we get something around 14 centimeters and divide all this by that magnitude, and we are going to end up with this. Okay, anyhow, F13 dot delta S, well, we've already calculated that. That's 23 Newton centimeters, and the magnitude of delta S, as I said, is approximately 14 newtons. Now, we've got a pretty good approximation here. This probably isn't going to come out with exactly the correct, corresponding exactly to the correct angle. And if we multiply F13 by the cosine, the magnitude of F13, which is 7.5 newtons, times the cosine of 77 degrees, probably going to come out with something a little different than this. But if we do that calculation, this will be equal to approximately 1.7. Divide this into this. 9/14 is pretty close to 0.7 because 14 times 7 is 98, close to 100 and all that stuff. We multiply that by the 0.67, 0.74, and we get something that's close to now I'm having a problem with my units, and I'm going to have to stop and not puzzle that out on my on screen here. I was careless in writing down my units here. The magnitude of delta S, of course, is in centimeters. You know, the magnitude of this vector is obviously in centimeters. So we're dividing the newtons by centimeters. So I get 1.7 newtons times this. And then this, when multiplied out, gives us about 1.14 newtons, 1.24 newtons, approximately. And that's actually the same as we got before when we projected F13 onto the unit vector. Projected F13 onto the line parallel to F13, because that line is going to be the same as the line parallel to delta S. And units don't matter, because the only thing that matters about that line is its direction and the fact that it goes through this point. Okay, so here's our projection of F13 onto delta S. Okay, now I'm going to call this the component of F13 in the direction of delta S, and I'm going to notate that F13 parallel, the two little parallel lines here are the geometric notation for parallel, and we read that as F13 parallel. I'm not speaking specific. I'm going to actually take the time to write this on the board. So this is projection onto delta S of F13, and I realize I'm running pretty short on time here, so I am going to pause for a second. Okay, I've made a couple of changes to a couple of things. I put an arrow over this. I put an arrow over component, okay, because this is a vector. This is a vector, so this component is a vector, and this needs to be designated as a vector. And up here, I've got magnitude signs, absolute values around these things, and these are vectors. So let's keep the notation consistent. Okay, so my projection on delta S of F13, which is this vector, I'm not going to read it to you, has a magnitude, and the magnitude of this is 1.7 newtons. So if I multiply the magnitude of this projection by the delta S, that's 1.7 newtons, it's a little messy, times 1.4 centimeters. And what's that equal to? Well, that's equal to about 2.4 or 24 Newton centimeters. Well, that's close enough to this. These two results are really the same. We're just doing round off and estimates here. The 1.7 is a little high. And we can also easily verify that if we just take the dot product of this vector with our entire delta S, we get this, and that it equals approximately 24 Newton centimeters. The fact that this is a little bigger than this is just because I was pretty rough in my approximation of 23 divided by 14, which is closer to 1.67 than to 1.7.